Hello everyone. In this video we're going to learn about some special polynomial products that are encountered quite often in mathematics and other mathematically related classes. So we want to become very efficient in handling them. In the previous video we learned how to multiply polynomials, but some types of these products are encountered so often in mathematics and its applications that it'd be very handy for us to be able to handle them quickly and efficiently. So we give them the name special product for that purpose. The first group of special products we're going to look at are the ones that are squares of binomials. Here you can see we have a binomial f plus L that's being squared, and here we have f minus L being squared. So this is the formula that we're going to be using to handle these, and of course where it comes from is very simple. If we simply do a quick tabular multiplication, we can see that f times f here will give us f squared. Here f times positive L will give us plus fl. Here positive L times f gives us another positive fl. And finally this L times L will give us positive L squared. And of course if we combine those two, that's where the 2fl comes from. So we get f squared plus 2fl plus L squared. Similarly, here we have the same situation, except here we get f squared, and then for the next box we get minus fl, because it's positive f times negative L, right? And similarly here, we're going to get negative fl, and in the last box we get negative L times negative L, which is going to be positive L squared. So when we combine those two, that's where the negative 2fl comes from. So this is our formula for the square of a sum. This is our formula for the square of a difference. And because this expression here is the square of this binomial, the perfect square of this binomial, and this expression here is the perfect square of this other binomial, those two expressions are known as perfect square trinomials because they're the perfect square of these two binomials. So we'll see that term before, so it's good in the future, and it's good to be familiar with it. All right, so for this first example, we're going to use the formulas that we just learned to go ahead and find these expansions. Notice that we already know how to do this using a table, but we want to do it using the quicker shortcut kind of method of the formulas that we just learned. So we know that the formula tells us that f plus L squared equals f squared plus 2fl plus L squared. So that's what we're going to be using here. Notice that here our f is going to be the first term, which is 3x, and L is going to be the second term, which is 2. So now we're just going to apply this formula. So f squared is just going to be quantity 3x squared plus 2 times f, which is 3x, times L, which is 2, and then plus L squared, which is of course 2 squared. I always recommend writing this formula down and then applying it in order to minimize chances of making an error. So here we get 9x squared plus 2 times 3 is 6 times 2 is 12 times x is 12x, and then plus 4. So here is our result obtained using the special formula which we learned for squaring a binomial. That's what we call that kind of a mathematical expression. That's the square of a binomial. All right, so for this one we're going to use the same kind of method, but notice we're going to use the square of a difference formula. The square of a difference formula, if you recall, is quantity f minus l squared equals f squared minus 2fl plus l squared. Here notice that what's playing the role of f is the first term 4u, and what is playing the role of L is the second term, which is 5. So now we're going to get f squared, so quantity 4u squared minus 2 times f, which is 4u, times L, which is 5, and then plus L squared, which is of course going to be 5 squared. Sometimes students make the error of using -5 for L. No, L is actually just 5 itself. It's just that you use this different form, which is the square of a difference, and the negative gets taken care of in the second term. Okay, so we end up with 16u squared minus 2 times 5 is 10 times 4 is 40, so 40u plus 25. A nice thing to do would be to double check yourself by doing the same problems quickly in a table, just to make sure that everything went well. Okay, so if you recall, for the table method, we create a table, we put one polynomial horizontally, the other one vertically, and we just multiply it out. So we get 9x squared plus 6x, just like a times table. So plus 6x plus 4, and of course we notice that we can combine these two like terms, right? So notice we get 9x squared plus 12x plus 4. So we just verified that first result, and we can of course do the same thing here as a quick check. This is of course not mandatory, but if time permits, highly recommended. So 4u minus 5, 4u minus 5, and then we'll just multiply it out. So here we get 16u squared, and that's going to give us minus 20u. That's going to give us another minus 20u, or negative 20u rather, and plus or positive 25. Okay, so we also notice that here we have two like terms that we can go ahead and combine. So we get 16u squared minus 40u plus 25. So there we have verified that our new method works well. Okay, so anytime you have extra time on your hands, you should definitely go ahead and do a quick check with another method that you may know of to make sure that no error has been made. So make sure that you can handle those, and then we'll proceed. Real quickly before we go away from this problem, however, I want you to always be aware of the error, which is one of the most common errors in mathematics, which is to see the square of a binomial like quantity f plus l squared and saying that's equal to f squared plus l squared. Of course, that is completely false, and this is not true. So basically, of course, not in general, right? In some rare instances it may end up being true, but in mathematics, for us to consider a statement to be true, it has to always be true. And given that this fails in most instances, we consider it to be a false statement in general. So basically, make sure that when you see 3x plus 2 squared, make sure you don't make the mistake of saying, oh, that's 9x squared plus 4. You'd be surprised how common that is. This is, of course, the correct answer. And of course, no difference when it comes to f minus L case, the quantity f minus L squared. This also is not f squared minus L squared. So when you see 4u minus 5 being squared, you don't want to say that's 16u squared minus 25. As you have seen, that is completely false. So make sure you don't fall for these two very common errors. Of course, the reasons students do make these errors, because it actually does work for multiplication. If you have f times L squared, that is f squared times L squared, and if you have f divided by L squared, that also is f squared over L squared. So this is the reason why students want to carry this over to addition and subtraction, and of course that's where the problem lies. What works for multiplication and division does not always work for addition and subtraction. So be very, very careful regarding this common error. All right, so here's a slightly more interesting one. Here you want to be extremely careful not to distribute the 3y cubed, because exponentiation comes before multiplication. So we have to take care of this power first. And of course, we can take care of that power using the special product f minus L squared. Okay, see, I try to practice what I preach. So every time you use it, just jot it down and you'll know it in no time. So you get that. So here the role of f is going to be played by 5y, and the role of L is going to be played by 6. So the 3y cubed we just carry. So we get 3y cubed times f squared. So that's going to be 5y squared minus 2 times f, which is 5y, times L, which is 6, and then plus 6 squared, which is L squared. Notice I used parentheses within parentheses. You can do that, just make the sizes a little bit different. Or if you want, instead of parentheses, let me show you, you could have used brackets. That's fine too. But either way, in more advanced classes, usually we just use different size parentheses. All right, but this is fine too. Okay, so we get 3y cubed. Now I'm going to go ahead and change it to parentheses because we're going to be done with those inner ones. So we get 25y squared minus 60y plus 36. Okay, so now that we've taken care of the squaring of this binomial and we're done with the exponentiation part, we can go ahead and multiply, which in this case, of course, means distribute. So we're going to get 3 times 25, which is 75, y to the 5. Remember, we're using the product rule, which says if you have x to the m times x to the n, that's x to the m plus n. So that's why we're adding the 3 and the 2 to get the 5, and they have the same base. And then minus 3 times 60 is 180, y to the power of 3, and this is y to the 1. So 3 plus 1 gives us 4. And then plus, that's 108, 3 times 36, y cubed. And that's it. We just went ahead and finished multiplying that all out. Okay, so be careful with these. All right, so here we have another example we could apply the rule to, because as long as we have a sum or a difference that is being squared, we can use the rule. So again, we know that the rule is f minus l squared equals f squared minus 2fl plus l squared. Here, the role of f is being played by 2/3 a, and the role of l is being played by 4/5 b. So sometimes, instead of taking all this so seriously, you just have to look at it like one of these games that you may be playing on your computers, etc. Each game has some rules. You learn the rules and you play the game. So here we have this rule that we're going to be applying, and we're going to end up with f squared. We know f is 2/3 a, so we're going to be squaring 2/3 a. Make sure you parenthesize the whole thing, and then minus 2 times f, which we know is 2/3 a, times l, which we know is 4/5 b, and then plus l squared. So l here is 4/5 b, so we're going to parenthesize that 4/5 b and then square it. So now we know that 2/3 squared is going to be 4/9, so we get 4/9 a squared. Remember, every factor has to get squared if it's in a group like this being squared, minus, now here we're going to see if we can do any cross canceling, and we notice that none is possible, so we go ahead and multiply across. So 2 times 2 is 4, times 4 is 16, over 3 times 5 is 15, and then that's going to be times AB, and plus, now 4/5 squared, we know that's 16 over, this whiteboard is not as under control as the ones in the classroom. Okay, so plus 16 over 25, and we're going to square the b as well. And that's it. We're done with that. So it's a really, really nice rule to know, and especially know how to use and apply. So make sure that you get comfortable with these rules before we proceed. Okay, in this problem we have the square of a sum, so we're going to be using the f plus l squared formula, quantity f plus l squared, of course. So we know that that's f squared plus 2fl plus l squared. Definitely try this on your own, pause the video and then come back to see if our answers agree. Welcome back. So here is f. F is being played by x cubed, and L is being played by y cubed. So we're going to get f squared. So f is x cubed, so we're going to put x cubed within parentheses and square that. So that's going to be f squared plus 2 times f, which is x cubed, times L, which is y cubed. We can put a dot like we put here, or we can actually put nothing. That's fine too. So, and then plus L squared. So plus, we're going to parenthesize L, which happens to be y cubed, and then square. And now we're just going to simplify. So we get, now here we're going to apply the power rule. We know that if we have x to the m to the n, in other words, when we have a power of a power, we keep the base, we multiply the exponents. So we get x to the 6 plus 2x cubed y cubed plus y to the 6. And that should pretty much handle it for us. So there it is. That's how we can apply this formula, the square of a sum formula, to get this perfect square trinomial. All right, in this example, we see that we have the fourth power of a sum. We know what to do if we have the square of a sum, but we haven't come up with a formula for the fourth power of a sum. So we're going to utilize the fact that we can rewrite this as x plus y squared times x plus y squared in order to get the job done. So we do have a formula for the square of a sum, which we know is f squared plus 2fl plus l squared. So here f, of course, is being played by x, and the role of l is being played by y. So we know that quantity x plus y squared is going to turn into x squared plus 2xy plus y squared. We're just applying this formula with x instead of f, y instead of l. So of course, if we do it again, we get the same thing. So here we also get x squared plus 2xy plus y squared. So now we have a trinomial times a trinomial. As you probably know by now, my favorite way of doing those is using the table method. So we're going to make a nice large table. We will list one of those polynomials terms going vertically down, so x squared plus 2xy plus y squared, and we can write the other one horizontally across like this. Then we'll go ahead and make our grid. All right, so x squared times x squared, that's going to be x to the 4. X squared times 2xy, that's going to be positive 2x cubed y. X squared times y squared, that's going to be positive x squared y squared. Here we have 2xy times x squared, so that's going to be positive 2x cubed y. The product of those two terms will give us plus 4x squared y squared. Here we're going to get positive 2xy cubed. For these two, we end up with plus x squared y squared. For those two, the product is positive 2x y cubed, and for the last two terms, the product will give us positive y to the 4. So now we notice that we have some like terms that we can combine. Right there we have 2. We have 3 in the middle here, and we have 2 like terms here that we can combine. So when we do that, so we start with x to the 4, which is not like any other term, so it's going to carry plus 2 of those plus another 2 gives us 4 of those, so 4x cubed y. Now here we have 1. Remember, if no number is written, the coefficient is 1. So we have 1 plus 4, which is 5, plus 1, which is 6 of the x squared y squared terms. So plus 6x squared y squared. Here we have 2 and 2, so 4, so plus 4x y cubed. And then finally plus y to the 4. We did it in a table, so we know we've already combined all like terms, so that should be our final result right there. So really simple, but you know, you just have to be careful not to rush. Most importantly, x plus y to the 4 is most certainly not equal to just x to the 4 plus y to the 4. That would be completely wrong. You would be missing those 3 terms if you were to make this common mistake. Okay, so make sure you can handle this. without looking before you continue. Another interesting product that is encountered often is when you multiply the sum of two terms by the difference of the same two terms. Now, if you have the sum of two terms and the difference of the same two terms, these two expressions, this sum and this difference, they're called conjugates of one another. So when you multiply these conjugates, something interesting happens. So look, let's multiply it out in this table. Notice f times f, that's just f squared. F times negative L, that'll be minus FL. Positive L times F will give us positive FL. LF or FL, same thing by multiplicative commutativity. And the product of positive L and negative L will give us minus L squared, like that. Now we notice that this time these are like terms and they do combine, but since they're opposites, they combine to give us 0, meaning they cancel out. So we just end up with f squared minus L squared. Now, make sure that you recognize the fact that whether it's a sum first, then a difference, or a difference first times the sum of the same two terms, makes no difference. You end up with the same rule, f squared minus L squared. So the way that we say it in words, we say the product of two conjugates. Remember, these are called conjugates of each other. The product of two conjugate yields, that means is equal to, a difference of two squares. So that's how you can remember it in words to help you remember the whole rule better. Let's go ahead and apply it. Remember, the rule can be used anytime you have a product of two conjugates, f plus L times f minus L. And we know that's going to be a difference of their squares. So, do we have that here? Of course, we have the sum of two terms and the difference of the exact same two terms. So what are those terms? Well, f here is x and L is 7. So according to the rule, we're going to get f squared minus L squared. So we're going to get x squared minus 7 squared. So we get x squared minus 49. And that's that. All right, so can we use it here? Of course, it doesn't matter if the difference comes first and then the sum. As long as you're multiplying two conjugates, you can use the rule. Okay, so here we're going to get f squared. Now, f here is being played by 3u. The role of L is being played by 4v. So we're going to get f squared, or quantity 3u squared, minus L squared. L is 4v, so we have to quantify that too within parentheses, otherwise we don't get the right answer, because we want to make sure both the 3 and the u get squared here, and both the 4 and the v get squared here. So we end up with 9u squared minus 16v squared, and that's all we need to do. How about these? Of course, anytime you have a sum of two terms times the difference of the same two terms, right? You can use the rule. So here, you just need to determine what's playing the role of f, what's playing the role of L. Notice the role of f here is being played by 2x cubed. The role of L is being played by 5. So we're going to get f squared, now remember f is 2x cubed, minus L squared, so that's going to be 5 squared. So remember here you got to square both of those factors, so 2 squared will give us 4. X cubed squared, remember we use the power rule, x to the m to the n equals x to the mn. So you get x to the 3 times 2, which is 6, minus 5 squared, which is 25. and that's all you need to do there. Okay, so really simple, really straightforward. Just have to be careful not to make careless errors. This should be very easy for you. All right, so we'll just do some problems involving the various rules we've learned today. Oftentimes they won't tell you what formula to use, so you need to be able to determine that. Here, of course, we have the square of a binomial. So we have to recall the rule f plus L, quantity f plus L squared equals f squared plus 2fL plus L squared. You can memorize these formulas like you memorize anything else. Use index cards, whatever it takes. But we do need to know these formulas for maximal efficiency. All right, so here we can see the role of f is being played by 1/2 x, the role of L being played by 1/2 y. You always get the people with the school of thought that says, look, nowadays there are all these devices available, etc. Why do we need to burden the mind and memorize any kind of formula? Well, because when you do, as you proceed with these kinds of problems, you're just going to be so much quicker, so much more efficient, rather than constantly having to, you're going to be so much more independent rather than constantly having to depend on looking for information. So yes, there's a little bit of effort in the beginning, but it pays off for a very, very long time for you. So here, we're going to apply the formula using 1/2 x for f and 1/2 y for L. So we start with f squared, so that's going to be quantity 1/2 x squared. You may have noticed I use the word quantity. That's when you don't want to say open parentheses and then something and then close parentheses and then square. The shortcut for that is just to say quantity. Now, if you just say 1/2 x squared, this is 1/2 x squared. So you have to be careful. Either say open parentheses 1/2 x close parentheses squared, which seems kind of not very efficient, or you can just say quantity 1/2 x squared. When you say quantity, that means that you're giving the listener the clue that they should open parentheses. Then you say your expression, so quantity 1/2 x. So how does your listener know that they have to close the parentheses? Because you mention an operation. You say quantity 1/2 x. The moment you say squared, that means go ahead and end the quantity and apply the operation that you're hearing about. So here we have quantity 1/2 x squared plus 2 times f. So 2 times. Now here you can use parentheses or not. It's kind of optional. If there's no negative involved, you don't really have to have parentheses. You can just use 2 times 1/2 x times 1/2 y. That's 2fL plus L squared. L again is more complex, so we need to quantify it. So 1/2 y, quantity 1/2 y squared. So now we know that 1/2 has to get squared. So 1/2 squared is going to be 1/4 x squared plus, here we notice that this 2 will cancel that 2. So we just get plus 1/2 xy plus, again, 1/2 squared is 1/4 and y squared is of course just y squared. So we get plus 1/4 y squared. And that's all we need to do. So there it is. Make sure you can handle that before we proceed. Now here's a problem I definitely want you to try before you come back to see if you did it the way that I'm going to do it. But just to give you a hint, it's one that can be done quite efficiently if you know the rules that we have studied today. And it's nice because it'll use more than one of the rules. All right, so I hope that you've tried it on your own. Now, Of course, you could use the square of a binomial formulas for these two, but it can be a little bit more interesting if you realize that you can always rewrite this as x cubed times x plus 1 times x minus 1 squared, like that. So now, why would we want to do that? Because we know that these are conjugates. And of course, remember, this expression is exactly the same as this, because if you were encountered with this, you would know that you would have to square each of these two factors, right? They're binomial factors, but you get this, right? So they're the same thing. But notice x plus 1 times x minus 1, we know is in the form of the product of conjugates, f plus l times f minus l. We know that gives us f squared minus l squared. So here we're going to get x cubed times, for x plus 1 times x minus 1, with f equal to x and l equal to 1, we just get x squared minus 1, right? But remember, we have to square that. So now we're going to use the square of a difference formula. So the square of a difference formula is f minus L, quantity f minus L squared equals f squared minus 2fL plus L squared. Here we have a different f here is x squared, and L here is 1. So we're going to apply this formula for this f, x squared, and for this L, 1. So we get x cubed times f squared. So what do you get when you square x squared? You get x to the 4 minus 2 times f, which is x squared, times 1. So that's just negative 2 times x squared times 1, which is just negative 2x squared. And then plus L squared. Remember, L is 1, so L squared is also going to be 1. And now we're going to go ahead and distribute the x cubed. So we get x to the 7. Remember, we're using x to the m times x to the n equals x to the m plus n formula, the product rule. So we get x to the 7 minus 2x to the 5 plus x cubed. So we saved a lot of time by realizing that this can be written as this, and also noting the fact that we have conjugates here. That's what gives us the clue that we should probably do this for the best results. So, of course, some of you may have done this. You may have done x cubed times, went ahead and used the square of a sum formula to get x squared plus 2x plus 1, and then use the square of a difference formula to get x squared minus 2x plus 1, and then go ahead and take care of this multiplication using a table, and then distribute the x cubed. Now, you should try that. In fact, it would be a really good exercise for you to see that you will in fact come up with the same answer in the end. Okay, so that would be your project, your home project after the end of this video. And that pretty much brings us to a wrap on this video. So make sure that you practice all these, rewind whatever needs to happen to get it all done, and stay safe until our next video.